In episode 65, titled MDF/IDF Design, Maintainability, Cable Strategy, and Operational Reality, the focus is on the main distribution frame and intermediate distribution frame as the physical backbone of a campus, where the best logical design still fails if the closets are chaotic. Network diagrams often look clean, but the exam likes to test whether you understand the messy operational reality that lives in racks, patch panels, and cable pathways. The main distribution frame and intermediate distribution frame are not just rooms with switches, they are the places where cabling choices, labeling discipline, and environmental conditions determine how quickly you can recover from faults. When these spaces are designed for maintainability, incidents become manageable because technicians can trace paths, isolate failures, and make changes without guessing. When they are not designed for maintainability, every small change becomes risky, and every outage becomes slower and more expensive. This episode frames closet design as an availability and security issue, not as a cosmetic preference. If you can describe what makes a closet maintainable and resilient, you can answer a wide range of practical exam questions about campus infrastructure. Before we continue, a quick note: this audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A main distribution frame, often abbreviated as MDF, is the central distribution point where campus cabling and core switching functions concentrate, and where demarc aggregation often occurs. Demarc aggregation refers to the point where service provider handoffs and building services are brought together, such as internet circuits, wide area network links, and sometimes building management connectivity. The MDF typically contains core or collapsed core switching, routing, and security equipment that connects the campus to external networks and interconnects all intermediate distribution frames. Because so much converges there, the MDF is usually a high-impact failure domain, meaning a problem in that room can affect many buildings and floors at once. The exam expects you to recognize the MDF as the central hub for uplinks, provider circuits, and critical services, such as voice gateways or wireless controllers in some designs. It is also where cable management choices have the highest leverage, because the MDF often hosts large bundles of fiber and copper feeds to multiple closets. When you understand MDF as both central distribution and aggregation point, you naturally treat it as a space that requires higher standards for labeling, redundancy, and environmental control. The MDF is where your campus network becomes real in physical form. An intermediate distribution frame, often abbreviated as IDF, is a local closet serving floors or zones, acting as the access layer aggregation point close to the endpoints. The IDF contains access switches that connect user devices, phones, cameras, and wireless access points on that floor or in that zone. It uplinks back to the MDF, usually over fiber, and may also host local patch panels that terminate horizontal cabling runs from work areas. The IDF is where most day-to-day changes happen, such as adding ports, moving users, or swapping access points, which means it is a frequent site of human interaction and therefore a frequent site of human error. The exam often expects you to understand that IDFs are many and distributed, which makes standardization and documentation critical because you cannot treat each closet as a custom art project. IDFs also have environmental constraints because they are often smaller spaces and can overheat if overloaded or poorly ventilated. When you understand the IDF as the local service point, you can reason about why cable length limits matter, why labeling matters, and why access control matters. The IDF is where the campus network touches users physically. Cable strategy must be planned with growth in mind because cable pathways, labeling conventions, and run planning determine whether future expansions are easy or painful. Planning cable runs means choosing pathways that support additional cables without requiring disruptive construction, such as using adequate conduit capacity, trays, and risers. Labeling must be consistent end to end so that a cable's origin, destination, and purpose are immediately visible, reducing time spent tracing and reducing the chance of disconnecting the wrong circuit. Pathways should also consider physical separation and safety, avoiding routes that expose cables to water leaks, physical damage, or high electromagnetic interference areas where applicable. Future growth planning includes leaving slack and spare capacity in pathways, so adding new fiber or copper does not require tearing out existing runs. The exam often frames this as maintainability and scalability at the physical layer, where the correct answer emphasizes structured cabling, clear labeling, and intentional pathways. When cable strategy is ignored, expansions become emergency projects, and outages become more frequent because changes are rushed and poorly documented. A good cable plan is an availability investment because it reduces human error and speeds restoration. When you plan for growth, you are preventing tomorrow's outages during today's installations. Patch panels, racks, and cable management are not optional neatness because they directly prevent failures by reducing strain, reducing accidental disconnects, and improving airflow and access. Patch panels provide a stable termination point for horizontal cabling and backbone cabling, allowing moves and changes to occur through patch cords rather than by disturbing permanent cable runs. Racks provide physical structure that supports proper mounting, grounding practices as required, and consistent cable routing. Cable management, such as vertical managers, horizontal managers, and proper bend radius control, reduces the chance that cables are kinked, pinched, or stressed, which can cause intermittent errors that are difficult to diagnose. Good management also makes it easier to trace circuits during incidents, which reduces time to repair and reduces the risk of making the problem worse. The exam often tests this by describing messy closets with frequent issues and asking what should be improved, and the best answers emphasize structured management. Patch panels also support documentation because port numbering and labeling can be aligned to diagrams and records. When closets are built with disciplined patching and management, the physical layer becomes predictable and resilient. Uplink redundancy between the MDF and IDFs is a key resilience feature because it prevents a single fiber cut or single uplink failure from isolating a floor or zone. Redundancy can include dual fiber runs, diverse physical routes, dual uplink ports on switches, and sometimes dual MDF combination points, depending on campus design. The goal is that if one uplink path fails, the IDF can still reach the campus core through an alternate path, maintaining connectivity for users and critical devices like phones and cameras. Physical diversity matters because two fibers in the same conduit can be cut together, and that is not true redundancy even if there are two strands. The exam expects you to think about both logical redundancy, such as link aggregation or redundant uplink protocols, and physical redundancy, such as separate pathways through the building. Uplink redundancy also requires capacity planning because losing one uplink means the remaining path must carry the necessary traffic without becoming saturated. When you design uplinks with redundancy and diversity, you reduce outage probability and shorten recovery time. The MDF to IDF link is the lifeline of the closet, so it deserves high attention. A scenario where poor labeling slows outage recovery dramatically is one of the most common real-world failure patterns because technicians lose time simply identifying what connects to what. During an outage, speed matters, and unclear labeling forces teams to tone test cables, trace patch cords manually, and sometimes disconnect circuits to see what breaks, which increases disruption. Poor labeling also increases the risk of accidental damage because a technician may unplug the wrong uplink, disable the wrong port, or patch into the wrong panel. The result is a longer outage window and often secondary outages caused by troubleshooting actions. The exam tests this because it highlights operational reality, where documentation and labeling are control mechanisms that reduce mean time to repair. When labels are standardized and match diagrams, teams can isolate the affected path quickly and restore service methodically. This scenario also reinforces why labeling is not merely cosmetic because it directly affects availability outcomes under stress. In high-impact spaces like the MDF, labeling failures can multiply because so many circuits are involved. Cable length limits are a physical constraint, and exceeding them can cause intermittent errors that are difficult to diagnose because the link may appear up but unstable. Copper Ethernet has maximum length guidelines, and when runs exceed those limits, signal quality degrades, leading to errors, retransmissions, and sometimes link flaps that come and go with temperature and interference conditions. These issues are especially frustrating because the network may work most of the time and fail only during peak load, environmental stress, or certain times of day. The exam tests this by describing intermittent errors and by expecting you to consider physical layer constraints rather than only configuration. Exceeding length limits is often a planning failure, where an IDF is placed too far from endpoints, or where cable routing takes longer paths than anticipated. Correct design places IDFs strategically to keep horizontal runs within limits and uses fiber for longer backbone paths. When you respect physical constraints, you reduce the chance of hidden instability that wastes troubleshooting time. Overcrowded racks are another pitfall because they block airflow and maintenance access, increasing both thermal risk and human error risk. When racks are packed tightly with little spacing, cables become tangled, access to ports and power supplies becomes difficult, and technicians may have to move cables or equipment just to reach the device they need. Airflow suffers because cable bundles and poorly placed gear block intake and exhaust paths, leading to hot spots and thermal instability. Maintenance access issues also increase downtime because simple tasks take longer and mistakes are more likely under cramped conditions. The exam tests this by describing closets with overheating and frequent failures, and overcrowding is often part of the root cause. Overcrowding also reduces the ability to add new equipment safely, leading to ad hoc mounting and poor power distribution, which further increases risk. A maintainable closet has space, clear pathways, and predictable cable routing, not just devices stacked for maximum density. When you plan for physical manageability, you prevent thermal issues and reduce incident duration. Quick wins include standardized labels, color coding, and updated diagrams because these practices improve maintainability immediately without requiring large rebuilds. Standardized labels ensure every cable and port follows the same convention, allowing any technician to understand it without local tribal knowledge. Color coding can quickly differentiate functions such as uplinks, access, management, and voice, reducing the chance of unplugging the wrong thing during work. Updated diagrams ensure that what is documented matches reality, which is critical because stale diagrams can be worse than no diagrams by creating false confidence. The exam often rewards these quick wins because they address the human factors that dominate many physical layer incidents. Maintaining accurate diagrams also supports change management because new work can be planned with full awareness of existing paths and capacity. These practices also improve onboarding and reduce dependency on a single expert who knows the closet. When you standardize and document, you make the physical network easier to operate and more resilient. Operationally, coordinating facilities for access and environmental monitoring is essential because closets are physical spaces with locks, temperature constraints, and building systems. Facilities coordination ensures that the right people can access the MDF and IDFs quickly during incidents, that alarms are monitored, and that environmental issues like overheating or humidity swings are addressed promptly. Many IDFs are in shared building spaces, and access may be restricted or dependent on building schedules, which can delay response if not planned. Environmental monitoring is also critical because closets can overheat, and networking symptoms from heat can look like configuration issues unless temperature data is available. Coordinating with facilities also helps with preventive maintenance, such as filter changes, HVAC servicing, and ensuring closets are not used as storage spaces that block airflow. The exam expects you to recognize that uptime depends on facilities partnership as well as network design. A well-designed closet still fails if power and cooling are neglected or if access is blocked during emergencies. When IT and facilities coordinate, physical infrastructure becomes a managed dependency rather than a recurring surprise. A useful memory anchor is central, local, label, route, and maintain because it captures the purpose and practices of MDF and IDF design. Central refers to the MDF as the campus aggregation point with high-impact equipment and provider handoffs. Local refers to the IDF as the floor or zone service point where endpoints connect and changes happen frequently. Label refers to the discipline that turns a closet into an operable system rather than a guessing game during incidents. Route refers to cable pathways and uplink diversity that determine resilience and compliance with length constraints. Maintain refers to patch panels, cable management, airflow, and space planning that reduce failure probability and speed recovery. This anchor helps you answer exam questions because it points you to the real levers of availability in physical network spaces. When you apply it, you naturally evaluate whether a closet is designed for reliability or for short-term convenience. To apply the concept, imagine being asked to describe the MDF to IDF traffic path in words and focus on the physical and logical sequence from endpoint to campus core. A user device connects to an access switch in the IDF through horizontal cabling terminated on a patch panel, and the access switch forwards traffic toward its uplinks. Those uplinks travel over backbone cabling, often fiber, through defined building pathways back to the MDF, ideally with redundancy and diverse routes. In the MDF, the uplinks terminate on core or collapsed core equipment that routes traffic between VLANs and forwards traffic to external networks through provider demarc connections. Along the way, labeling and patching ensure each segment is traceable, and environmental and access controls ensure the closets remain stable and serviceable. This narrative is exactly what the exam expects you to understand, because it ties physical layout to network function. When you can describe the path clearly, you can also identify where failures occur and how redundancy is achieved. It turns topology into an operationally meaningful story. To close episode 65, titled MDF/IDF Design, Maintainability, Cable Strategy, and Operational Reality, the core lesson is that closets and cabling strategy are uptime controls because they determine how quickly you can recover, how safely you can change, and how often physical issues create intermittent faults. The MDF is the central distribution and demarc aggregation point, while IDFs are local closets serving floors or zones, and both must be designed for growth with planned pathways, consistent labeling, and maintainable layouts. Patch panels, racks, and disciplined cable management prevent strain and intermittent errors, while uplink redundancy between MDF and IDFs protects against cuts and device failures when designed with true physical diversity. Poor labeling slows recovery dramatically, while exceeding cable length limits and overcrowding racks create intermittent issues and thermal instability that waste troubleshooting time. Standardized labels, color coding, and updated diagrams are quick wins that improve maintainability immediately, and coordination with facilities ensures access and environmental monitoring are reliable. Your rehearsal assignment is a closet audit rehearsal where you walk through one MDF or IDF mentally, stating what is labeled, how uplinks are routed, where redundancy exists, and what environmental risks are monitored, because that rehearsal is how you turn physical design into operational reality. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.